and we had one day a sudden visit from Tamil Nadu State Electricity Board, and these people said, "Look, we were told by our director to come here to solve a problem." The director had just heard that there's a mathematics institute in Chennai, and said, "Go and ask them; they can solve this problem." So, what was the problem? So a lot of Tamil Nadu's electricity is generated through wind farms. Actually, I think we are the state which is the highest fraction of electricity generated through wind farms. The problem with wind farms is that it's famously unpredictable. And so you really don't know very well that in the next 24 hours whether it will generate this much electricity or not. So if there's a shortfall, you need to go to the power market and buy the deficit electricity, right? So the thing is, like all markets, if you buy in advance, you get it cheaper. Whereas if you go and buy it at real time, then the price is much higher. So they want to know at least 24 hours in advance how much power to buy. So then they'll get a cheaper thing. So what's the problem? The problem is that you need to know how much shortfall will be there, and so therefore you need to know how much power you'll be able to generate. Let's say 1 day in advance. So therefore you need to know how much wind will be there. So what will you do? You go to some prediction, some climate prediction company, right? The problem is none of the services, so they buy. They don't have their own in-house prediction thing, so they buy it from one of these international agencies. Actually, they get it from 5 different agencies, and none of them are correct all the time. So some of them are correct some of the time. The problem is who is correct tomorrow? They have no idea. So they say, okay, we are already buying this data, so you don't have to, set up a climate prediction model yourself. Can you actually, using this data, be able to tell us with better accuracy than any of these things, which one is working? And so, since Anuran was free at that time, I mean, okay, he was working on dilemma, but everybody else was juggling with 3-4 problems in my group. He was working with only one problem. So I said, Anuran, can you please look into this? Did I say like this?
No.
Anuran! Which one? Okay.
Somebody different.
Okay. So anyway, so Anuran decided to go the neural network thing. So he said, what if I do like this? I feed the neural network the previous history of the predictions from these 5 companies and what actually happened on that day, and then train the network, and then now I will give it a new set of data and basically ask what. So basically you are, in some sense doing wisdom of crowds, well, wisdom of experts. Crowd of experts. No time series analysis. Where's an okay. No time series analysis. No ARMA, no Gantt. Okay, it's depends upon your taste. So anyway, so long story short, that's how he cut his teeth on neural networks, and I must say that I'm really impressed by what Anil achieved in that. And then he got really interested not just in the applications of neural networks, but on whether you can understand what's happening inside neural networks. So it's a great pleasure to get him to speak on
Thanks a lot.
how to optimize using networks.
Did the electricity board like the did the electricity
The electricity board sent data later, which was duplicate. So, they sent another data saying that this is the data for the next year, but it was the previous year. So they were not serious about it. Unfortunately. But fortunately, I got into this.
So they only came here because they directed it.
Yeah, yeah.
I'm hoping they won't see this. I'm gonna always get Gayatri to delete that part.
All right.
Sorry.
Yeah. So, well, we heard the first neural network talk by Siddhabra, and today we'll look at just optimization. There won't be much learning. There will be mostly optimization, and we'll realize what is the difference between them in some time. So we will focus on the traveling salesman problem, but this is an example of a large class of problems called combinatorial optimization problems, right? And there are others like graph partitioning that Shakti touched upon. Then there's image processing and other things that you can actually attempt with a neural network, more likely a Hopfield network. So let's dive right in traveling salesman problem, right? So we're given this setup, right? We have a couple of cities or couple of nodes which have to be visited in a certain sequence so that one city is not visited twice and the full path returns to the original city, right? Yeah. So the only given information is the distance matrix. So you realize that I think 2 talks before Anindya told us something about distance matrix, so it is sort of loosely related to that as well. Like if you have a distance matrix and you have to find a sequence such that every node is visited once, right? So an example is these two. That is a good path because it sort of reduces the path. So this is an Euclidean space, right? So 2D Cartesian coordinates, right? And that is a bad path for obvious reasons. So since we're taking Euclidean, there can be much more generalizations, right? Making it non-Euclidean, then asymmetric distances, like you're going from city A to city B, lot of traffic, B to A, not a lot of traffic, right? So there might be a lot of variations, but let's stick to the plain and simple vanilla one, right? So this has been attempted. This is a benchmark problem in combinatorial optimization. So people come up with algorithms and then they try to see how good it's working on this problem, right? Okay, so let's try to feel what the problem is, and so we'll start with a game, empathy for the network, right? We have this distance matrix, and so the objective is to find a path through it. So let's think of it a little more clearly. There are 5 nodes here, right? There are 5 nodes and sequences like this, and it's going to return to the first city, so it will be a in the end, and so it's like a cycle, right? So how many combinations are possible in this? There are 5 in number. Correct. How many unique? So what are the degeneracies possible? So you can have flip, right, and that will give you the same path. You can have one shift operator, right, which shifts like you E, A, B, C, D. That's also a valid path and it's the same path, right? So how many of these do we have? One is reflection, another is shift. So 2 into whatever number it is. In case this is 5, in this case it's 5, right? So for a general problem you have n cities, then n factorial total possible paths. Number of unique paths, let's say, is x. So 2 into n into x will be n factorial, right? So number of unique paths will be n factorial by 2n, or n minus 1 factorial by 2. So let's look at our problem. 5.
And what is x?
X is the unique number of unique paths. Yeah? Clear till now? All right. So we have 5 cities. So how many unique paths? So 4 factorial by 2, which is 4 factorial is 12, but by 2, so it's 6. Oh, I'm so sorry. 12. Sorry, what? 5 minus 1, 4 factorial, 3 into 2, 6, 6 into 4. Yeah, sorry, apologies. Alright, so we have 12 paths. So now, with all this in mind, start from a random city and try to minimize the distance. Any suggestions? Oh, if I go out, you'll be able to see the answer. Oh, I didn't think it through. Okay, fine. So any suggestions of a possible path? Let's start from B. AC. ACDBE. Any other? ACEDDB. All right, there are only 12. I'll take these two, and so let's look at what the path is like. I hope, like, let's not. Shit. Oh no. Oh god, that was close. Did you guys already look at the answer? Okay, fine. Doesn't matter. So, can you see? Yeah, you can see. Oh, am I in the wrong? Oh, it's actually in the wrong place. This is what happens when. Hey, Kalani, how did you run? Control Enter. Fine, you guys already got the answer. Fine, it's ACEBD. So one answer is ACDBE, ACDBE. So you see how messed up of a route that is, right? Then you have ACEDB, ACEBD. Very close, very close. But so you realize that it's a very like not very obvious. If you think like what path should I take next? So I can give you an example. Like you have these cities, right? You start from here. What's the closest? The closest is this, right? Okay, let's start like this. You start from here. What's the closest? It's this, closest, this, and then it has to go here, right? So this will be the shortest route, right? But that's not always the case, right? So if you have this in a line, or like it doesn't also have to be in a line. So you start from here, and you go here, here, and then you have to go this far, right? So it's not always going to the next closest one. So there was another one which was the harder one, but since you guys already failed in the easier one, I'll just so you see it looks really complicated, and single like next step is smallest won't really give you a good answer. So you have actually have to think incoming link and outgoing link, both sort of have to be minimized. So the answer to this would have been that one, and you see the issue, right? DF is the smallest, but it's untraversed. All right, so this is what we're dealing with a neural network, right? So this was initially 1985 or 4, Hoffield and Tank proposed a particular architecture for solving these sort of traveling salesman problems, which looked like this, right? So a salesman has to travel through n cities, and you have n stops as well. It has to make n stops to make the entire tour, right? So you have this network of n square units where city A is visited in the third stop. Sorry, city B is visited in the fourth stop. So that's how we're gonna think about this particular scenario, right? So here the tour will be CABD, or it can also be EABDC, because you can shift it, right? Yeah. So what are the constraints that so it's a very general neural network, and any so as Siddhartha sort of focused very nicely on, is that neural networks essentially can be thought of as spin systems, and here we can think of it as an energy, right? We have to minimize the energy for the network so that it reaches a particular minima or the optimum solution in this case. Yeah. All right, so what constraints do we have? A city is visited exactly once, right? That's so a city is visited exactly once, so A has to be visited exactly once. So in this entire column there should be one unit which is on, all the others should be off. Similarly, at a particular stop it cannot be in two cities at the same time, right? So in a column only one will be on. Yeah, makes sense? So those are the two constraints, and What is the actual information of the network? It's the distance traveled, which we get from the D matrix, distance matrix, right? Which you guys try to evaluate as well. That is here. So these are the two constraints for it to be a valid traveling salesman tour, and this one is the cost, which will essentially tell you that this is the shortest tour, right? Now do observe, like this is not v y I plus 1 and that's it. There's a negative term as well, like so it doesn't do the next shortest one. It's actually looks at both sides, incoming and outgoing. But anyway,
What is Y?
y is oy. I am very sorry. So here the notation is like v x I, yeah, it's over there, no? So one stop vxi is equal to 1 if tour has made stop at x, made visited city x at stop y I, right? So similarly vyj is essentially city y at the jth stop. So that's how my vxi's are defined. So you realize it's not a n neuron network, it's a n square neural network.
So it's like a delta function.
Yeah, this is binary. This is entirely binary. Right now we will touch upon the continuous part of it later, but this is, for now, it's binary. Yeah. Any other questions here? Dx by, you guys get it, right? Distance from city x to city y and y to x. Similarly, like we are considering symmetric. Yeah.
What was the original motivation for this problem? Was it like just a puzzle, or there was some specific motivation?
So traveling salesman problem is sort of like a benchmark tool for yes, optimization problem. So this neural networks are learning, like these are systems which can do learning as well as optimization. Like optimization and learning is like comes in differently by,
So neural network. Just asking what
yes.
traveling.
So I could have taken graph partitioning as well, or I could have taken any other optimization problems. The motive here is to show that neural.
What was the motivation for proposing the traveling salesman problem? Like whoever proposed it was
I think they wanted to show that neural networks, Hopfield and Tang, they wanted to show that neural networks can do optimization as well. So that's why they chose traveling salesman. Like
I'm asking even before that. I mean,
why the traveling salesman? Oh, the history of the traveling salesman. So it was first around 1930 that it popped up. Actually, it came before that. Hamilton made a game, and it called that was sort of finding this particular tour, like a cycle. It's called a Hamilton cycle, and there this idea came, and then people did refer to these things in their notebooks, like how do I design a path, or for my, let's say, my grocery, or for supplies for some company or shop they have, like. So it was very informally understood that a problem like that.
from a practical point of view, that constraint one should not be since the problem.
Oh, I see. Yeah. Oh, yeah. So you can, if you think about the traveling salesman problem from scratch zero, it can visit. So I do understand, because you might have something like this. If you have asymmetric networks, then this way might be less, and this way might be more. So you can have sort of like a central node which is very well connected to the others, but all the incoming traffic flow is very heavy or very less. Yeah, outgoing is very heavy. So if you have asymmetric, then you can take the advantage of a particular node which has very fast flowing travel, and so you can revisit it multiple times to really lower down your time of travel, or not reduce the path length, but here lower the time of travel.
I think maybe avoiding process needing price advantage to improve the efficiency. Say like suppose I want to search in some space, like in the least possible time, least possible steps. What is it?
So I think this 1930 it came as formally as a school bus routing problem.
Also originally, even before Hamilton, there were handbooks that used to be printed which told travel salesmen where like you have to travel by carriage. So it was like a major hassle if you have already sold your stuff at some place. You don't want to go back there. Maybe because what you sold was had made the citizens irate. You don't want to give them a right worth. So there used to be these handbooks which told you what is the most optimal route, let's say for Switzerland and for Germany, covering the major towns. So then Hamilton was the first to make it happen. But it was only in 1930s that it was technically proposed in the proper form.
The top.
No, so then cost minimization becomes very difficult because you are traveling the same place.
Again, can you try to motivate why the cost of the path looks like this? I mean, I do not get why you're looking at the back thing and the ahead thing both of them. Like V y I plus 1 and V y I minus 1.
So
Yeah.
you realize in the exercise that we did right now that if you consider just the next path,
Yeah.
that's actually not very optimal, right? You start from here and you go to the closest one. Okay, bad example. I have to take another. You go to the closest one. The closest ones are these. You start from here, right? So you go here and then you go to the closest one and this. This is definitely not an optimal path, right? So most of the times what is better, okay, in this case it is an optimal path.
Yeah, you should have gone to.
I have to cook up an example properly.
You put 3 of them on a line, then maybe. Yeah.
Right. So that's why you don't. That's why, motivation for this sort of a cost is that you're not just going forward. You're also the total distance traveled to go to a city and go out from that city. So it can also happen like this, right? There's reflection is allowed. So, right?
Something.
Yeah. Any other questions? All right. So yeah, these are the one that makes it a valid TSP, these two constraints, and this constraint actually putting the distance information, distance metric inside, right? And that will, specific to a particular TSP traveling salesman problem. All right. So what kind of energy function can you make? This was initially proposed by Hoffel and Tank, 1985, and very simple-minded approach. So these can take only one value and 0, right? These two values, right? So if at a particular x, if the ith and the jth, so if you consider b, right? If the ith and the jth are on, then this will be 1, and that will increase the energy, right? So this term captures this one. This term captures this one, this constraint. This term captures this constraint. You can actually see, right? If you consider this line, this one, and if another stop is on, then it will contribute a value of 1, and so the energy will go up. So these two constraints are being captured here, and this one over here essentially tells you that there has to be n stops for n city. If it goes above, then because of this structure, it will contribute a positive cost. If it goes below, it will contribute a positive cost, right? So it has to be exactly equal to n. Number of active units in this network will have to be exactly equal to n. That is captured by this term. And then the final one is the d total that has to be minimized, right? So it's a.
So initially you did not have any condition on n in the original problem, and then when you are writing the total energy function like this, you need to.
There is a constraint on n, right? That is.
Yeah, that is what I'm saying. The first two term being satisfied would not imply.
Yeah.
Okay.
Because you see, if it doesn't visit anyone.
That's also okay.
Right. Yeah. So now here there are 4 parameters, and it becomes a bit of a tricky job to search, but we'll see. So how do you go ahead?
These are the Lagrange multipliers.
These are the.
Physics might want to know that
Yeah, these are same as the Lagrange multipliers. Yeah, where you have where you want to minimize the energy given a particular constraint. Yeah. D total is apologies. Yeah. So sum over all the, like, if you're visiting cities, what's the total path being covered? So
total cost.
total cost, yeah. So the distance dxy is multiplied by vxi and vyi plus 1, yi minus 1. So the next stop and the previous stop, right? For all x and y. Sorry.
So for a particular
Yeah, for all x and
what is the total cost?
Is it okay? Right? So this sort of gives you a feeling that you can practically cook up any energy function. You make a neural network, you cook up any energy function and try to see that if you have made the energy function correct, you can sort of go to your objective or optimize. All right.
Even the protein folding problem can be
Yeah.
used to this, which is what fetched the
Chemistry Nobel Prize. Yeah. All right. Okay, so we're going to attempt this particular problem, this energy function, and we want to reduce it using two methods. One is discrete, one is continuous. So let's go through discrete dynamics first. So the dynamics happens in a n square dimensional hypercube because this has n neurons, right? And they can take 0 and 1 values. So how many possible configurations? N square possible configurations. So it happens on an n square dimensional hypercube, right? This I hope you have encountered a couple of times in these past days. Boltzmann factor, right? And it essentially weighs the difference between the energies and gives you a probability on towards which state it wants to go towards, right? So the probability of having a VA configuration, right? This is the VA configuration and this is the VB configuration. Yeah. All right. So so when you're actually sampling the entire n square possible space, it's really large, right? So what you operationally do is you take individual nodes, individual neurons, and then flip it and see if its energy is lower or not. So that is sort of given by this, and you can actually work it out and show that you can go from there to here just by considering VA and VB differ by only a single unit being on or off, and you will be able to arrive. Okay, fine, I'll just, how much time should I? Okay, 5:45.
does the denominator follow your constraint? There are two dots on the.
Very good. We'll come to that. It doesn't follow the constraint. So it essentially is like in the first, the above one is probably somewhere here, and the second one is here, or maybe like higher in the energy landscape. So will it accept?
Oh, it's like visiting a city twice.
Huh?
Which
Yes, it's visiting a city twice, and that incurs a cost because of that term in the energy, right? Yeah. So yeah. So okay, let's touch upon that a little later. A couple of slides later. No, like couple of minutes later. So yeah, so if you have PVA by PVB, right? So you can do essentially this. I want to find probability of VA properly, right? So, and it's a single unit, VXIA, whose VXI, A is the configuration. So VXI, are the indices too much to handle? Oh, anyway, so VXI being on or off, right? So two possibilities. So it's essentially P, you can write it as 1 plus this thing, and you'll essentially get PVA plus PVB by PVB. Flip this, and you get PVB, because PVA plus PVB equal to 1, right? Because we're considering only one. What is the probability that the state is in up or down? It's 1. Right?
First line 1 plus b.
Oh yeah, I just added it. So you have this exponential term, right? E to the power, e to the power minus delta e. Like let's consider delta e. Okay. E to the power minus delta e, right? So you add a 1, and you do a reciprocal, and you arrive at this. Right, so it's very easy to go from there to there. Where that picture is essentially you have two random states, and what is the probability, and this one is you take a spin, flip it, do you accept it or not, depends on this. How does this function actually look like? You guys have come across this multiple times. No, I mean you have, I suppose. Yeah.
The equality sign in the first equation.
Oh no, it's not equal, sorry. Yeah, I added one. That's what he. I'm sorry, bad. Like I'm just trying to go a bit fast. Yeah, so the function essentially looks like this, right? If you plot it, you'll be able to see it. If it's positive, so here, if the delta E is positive, then it goes to 1, right? If it's negative, it goes to 0. So the probability of that state flipping is essentially a sigmoidal curve. But anyway, that we'll touch up more on that later. But as you pointed out, Akshay, is that this state is unlikely, improbable, right? Because this has 2, and that's why the energy or the cost will increase. So what do we do? So one thing that was proposed in 1983 by Kirkpatrick, Vecchi, and Gelat is that they took the example of a actual physical system, glass or metal. So when you have a very hot glass or metal and you just very fast cool it, quench cooling, I forgot exactly what it's called, you just put it in water, right? So everything which was like all the electrons and all the whatever like atoms they suddenly get cooled, and they sort of get stuck in that very unfamiliar, like energy, not unfamiliar, very rugged energy landscape, right? So you'll have this sort of a this was the situation in high temperature. They're all around, right? Because you see over here, if the temperature, so there's a delta E by T, right? This temperature, if this temperature is very high, then e to the power 1 by infinity, very high, so it becomes 1, right? So the probability of having any state or flipping is half and half. It doesn't care about anything else. If the temperature is high, it's going to flip up and down based absolutely on noise, right? So the system becomes extremely noisy, and it doesn't care about the energy landscape anymore, right? So if you cool the system right exactly then, right, it's going to be in a very frustrated situation. And so a practical example is that glass, if you just make it very hot, and then just drop it in water, the molten glass, it freezes and it becomes very easy to break because there's frustration in the system. But if you cool it very gradually, right, so you reduce the temperature little by little and then cool it, the system actually becomes more structured, ordered, and that contributes to the stability. So glass which is cooled like that is actually much less prone to breaking, and that was their motivation, and they put it in like proper simulations and models and in real life. So it can also be used in graph partitioning as well, which Shakti touched upon. It's used in traveling. It can be used in multiple areas, like wherever this sort of like wherever the temperature creeps in, right? Yeah. Yes, definitely. So there's an optimal rate at which you have to cool. There's an optimal temperature where the minimas are all accessible. If you go below that, you're stuck. If you're above that, you don't access anyone. So there are many nuances to this particular simulated annealing treatment, and it differs from problem to problem.
How should I know that? From experience?
Yeah, you have to play with it. You have to play with your problem with the simulated annealing technique, right?
A glass with a more crystal more ordered structure is less brittle.
Because there is frustration in the like suddenly cooled system, right? So one thing doesn't want. There are like possible pathways of fracture. Here there is no the possibility of having a fracture here is equivalent to the possibility of having a fracture here, right? But if you have that heterogeneity, there is probably a path where it can fracture.
Maybe a better example would from metal? Because glass with a crystal structure by definition is not glass, it's crystal.
Crystal, yeah.
So for metal, actually I mentioned in guidance class, right, that if you have worked hardening of metal, it becomes harder, more easy to break, because all of these crystal plates get misaligned. Right? So you get very hard and yet brittle kind of metal. So to make it again like more what do you call it?
Ductile. Malleable.
Malleable. Yeah. So you need to do annealing treatment. Best example of this is a samurai sword, which is made by
Right.
layers of
Right.
quenched and annealed layers.
Right. Yeah.
What are we learning from this picture? What is the goal? Is to add in maximum?
Yeah, this is maximizing. The problem we're doing is minimizing an energy, but here they're maximizing, let's say, modularity or any objective cost function. Here it's not a cost function, it's a benefit function, I guess, which is being maximized, right? So you see the temperature. When it's high, it's all over the place. It doesn't care about the energy landscape, it's all over the place because probability is equal to half. But as you lower it down, it's sort of like, stops in these very high regions, right? And
So if you just flip the thing, it becomes energy.
it becomes an energy landscape. Yeah. You just need to change it from a benefit to a cost. Yeah. That's what the representation is. So this is sort of like a visual representation as well. Like when you have high temperature, everything is daily. Yeah.
Do you think the optimum temperature is near criticality?
What is criticality?
Like some temperature AC transition.
Say that again.
So when you are annealing, you spend, so you can decrease it linearly in different ways, right? If you spend more time near the critical temperature, do you think you're more likely to get difference? I mean,
Yeah, I agree. That's why I said I don't know. I haven't played a lot with simulated annealing. This is, I think, my first experience.
So is there like a roughly, I mean, scale? Is there like that optimal rate scales with the system size? Something like that?
Could be. Yeah, could be. I'm not sure. I'm not very
I
sure.
mean, roughly, like, if I want to kind of, before starting a simulation, like, roughly idea of like what amount of time it should take. So, from a system size, can I make an estimate?
It will probably depend on system size, but I can't be very sure. I haven't done much of this. This is the first time I'm doing this. There are multiple types of schedules. Like you can do linear cooling, you can do logarithmic cooling, you can do exponential cooling. You can stop at different places. The one that he points out that if you stop at the criticality, I'm still sort of kind of new to annealing. So I was thinking, Rajesh was talking about this transition, right? So you have a very disordered material, 1D icing chain. Sorry, not 1D. Like you have an icing system, right? And you lower the temperature, not 1D. You lower the temperature, right? And after a certain critical temperature, it becomes ordered, right? So it was very highly disordered and become, but I'm not very sure if that is like if it is optimum at criticality. But yeah, there is definitely a particular temperature where if you pause for a while or you slowly change in that region, it is going to sample more of the like dip, like more of the like global minima, because the global minima is higher probability of being there, and less of the local minimas, right? So that is probably there, but I have not played with it enough to comment on that.
I mean, one can think of it this way: that below the critical point, the valleys start getting disconnected.
Yes. Below the critical point, the value starts getting disconnected.
Above the critical point, all the valleys are connected. Just if you go just below the critical point, some valleys get disconnected. Now, if you go lower and lower down, more and more valleys are getting disconnected.
So you would want to spend more time near the critical.
But it's not clear that that's the most optimal response. Right? Because you don't want to jump out of the lower minima if you manage to find it.
So high temperature, it's everywhere, right? Low temperature, sort of localized, but somehow like it can go to the other one. But low temperature just goes in, doesn't have like cannot come out because the temperature is too low. Hi. Here. I'm so sorry, I didn't put the reference here. This is Wikipedia. They didn't put anything. I don't know. I don't know what system they're doing here because this is a maximization on top. Yeah. This is energy, not energy. This is minus energy. This is minus energy because energy. It's trying to maximize it, not minimize it. Is it clear till this point? Right?
This landscape is also changing.
No, the landscape is not changing. The way the states are evolving, because you see, this energy is fixed with the dxy and all that d and vi, all those, it's fixed, right? The temperature is what's changing. So the energy landscape is fixed. It's the temperature which is changing. Like if you just look at this equation, right? Or if you look at this equation, right? The energy part does not have a temperature in it. It's the state dynamics. It's the state dynamics which has the temperature in it. So it's the state dynamics. So the energy landscape is the same. It's how the state is like evolving. Yes. So it's not the temperature does not creep into the energy. It's the state dynamics that is being influenced by the temperature.
We were just talking about this phase transition causing that
Yes.
the minima to get disconnected. That is what
So here you see the minima is getting disconnected here. There are minimas.
in the sense it won't explode that anymore.
Yeah, you won't be able to cross this barrier. The barrier is too high now. The temperature is not there to thermally take you to the other side. Right? All right. So we can try to do a simulated annealing sort of approach on this one, so that you see this is a bad step, obviously, as Akshay pointed out, that this column has 2 on, so it will be higher energy, but we can start with a higher temperature so that it can be crossed. But give me a better algorithm, like instead of having 1 on, like just randomly pick a node and turn it on or turn it off. There is a better algorithm, right? You should be able to tell me because you worked on it. Swap, column swap the columns.
But for that you need to be initially in one of these states.
Yes, you start with any arbitrary valid tour. If you start with a valid tour, the first 2 constraints are satisfied. Then you can swap it. The first 2 constraints are always satisfied, right? Is that clear? All right. So we are just swapping. So you see, I think here I've swapped second stop with fourth stop, right? Yeah. So the first 2 constraints are always satisfied. Now the only contribution to the energy comes from the distance, and this very high barriers are probably not there anymore. So even with this, you have to do something. You have to do simulated annealing to get these valid tours. So here this black curve, I don't think you can see the axes. This axis is temperature, this axis is path d total, and this is the iteration. So I'm doing this dynamics, I'm doing this dynamics, right? Selecting a path, selecting a state, like swapping it based on this probability, or based on this probability, and that is what my evolution looks like, the state evolution looks like, the black curve in both of these, right? So this is
What's that red line?
the red line is the temperature. I am reducing the temperature linearly, right?
Black and captures the state it explodes.
Black line captures the total distance in that particular state that is there in that iteration number. Is that okay? So you're doing a normal, like you can call it Monte Carlo, Gibbs, whatever it is. You're sampling, right? At every sampling step, you have a different configuration, and you're calculating the distance at that configuration. This is what's plotted, the distance at each iteration, and with each iteration, I'm reducing the temperature linearly, and it gives you a decent enough graph. It's not best because you can actually, from your intuition, see that this could have been better if this crossed here, and then this connected. So this would have been, this module could have been like better traverse, but this is what it did. That's I think that's a 15 city tour. This is a 25 city tour, right? Now that's discrete, and it does pretty well. You can do it with continuous as well. So in continuous, you have the same sort of structure, which is you have these n square units, but these units are not binary anymore. They're not 1 0. They are on the real line. So you have r n square space, extremely high dimensional, and so finding the optimum tour in this r n square is probably tricky, but there is a some people have found a way, which is let's first touch upon how do you make it continuous. Till now we have been touching on discrete and saying that probability of changing a spin or accepting a configuration is like that, but here you can also think of it in terms of evolution of the continuous evolution of the state using differential equations, and you guys will have already encountered Euler. There are other methods as well, but you can solve those differential equations with this, where the state variables are Vi and Ui is the input received, right? What do I mean by the input received? If you realize, here we went from this picture to this picture, right? This is the sigmoid, right? And this is what the input will be, and that's what we are capturing here. This dou E dou Vi, a better way of visualizing it is, that was delta E, right? And that was discrete space. That's why we took delta E. Configuration in this, configuration in this, take energy difference, delta E. You lower energy, you accept it, higher energy, you don't accept it with a certain probability. Here, it's continuous space. So, you do a sort of gradient descent, right? So, you're going towards the trajectory where your energy is being minimized, right? So, so we'll probably touch up a little on this later, but that's the kind of um, dynamical equation that you can use to solve the traveling salesman problem in the continuous space, right? Yeah. Now, there are caveats. This is one of the caveats. That is, in case of the dynamical system, in case of the discrete space, what we did was we started with a particular tour, right? And we can start with any tour, like anything, and then it will sort of go, because of swapping or exchanging, it will go towards a particular minima. But in case of this, since this is a deterministic system, what ends up happening is, if you start at one of the corners of the hypercube, this is a Rn square, but the solutions are at the hypercube, right? The solutions are at the hypercube corners. So if you don't start at the center, you start somewhere else, like pretty far away, then what happens is you don't go to the corners, you go to some plane, and it becomes problematic. Those are just nuances. We can talk about it later. Yeah, this was proposed by Brandt in 1988, where he just changed the cost function a little bit. So these two, if you realize, actually takes care of all the constraints. Lagrange. This feels a bit more Lagrange, yeah. What, are you judging me? Okay, fine. So this captures all the constraints, and this is your d total, which will be minimized, and that gives you tours like this, which was actually published there, and this is, I think, a 16 network, a 16 city problem. This is a 32 city problem, and you can see there are very suboptimal parts, right? There are pretty suboptimal. There's this path crossing, which is obviously bad, but it still does a decent job. So this just goes to show that Hopfield networks can actually also do optimization problems, but if you're actually thinking of just traveling salesman problem, there are way better algorithms. But Hopfield networks can also do different kinds of optimization problems. Yeah. With that, did I miss anything? Oh no, yeah, finish my thought.
Pretty good time. So I think to ask this one Do you think that if we insert some structure in the Hopper model, it will improve performance?
Yeah, could be because you see, if there is clustering, if there is some sort of a clustering on the city distribution, then I think it might. I can't. I don't know. It feels like it might be able to do a bit better. Yeah, but as we discussed before, this n square for an NCT problem, you're using n square is very wasteful as well. So it might be possible to use a modular sort of network to capture this clustering of cities.
But the clustering of the city, do I need to know exactly how the city is clustered to design the VLAN? Because if that is the case, then I will do it like specifically for each problem.
This someone has to work out.
That is a question.
Yeah.
Yeah. So, I mean, from what I understand, you did a Monte Carlo like simulation to solve this traveling salesman problem. Yeah, here. So, uh, do you have any idea of how the energy landscape looks? Because from what I've heard, at least, unless the energy landscape is sufficiently funnel-like, it's very unlikely you'll find the correct.
Yeah. So here, in this particular problem, it's extreme. No, this particular approach where you're flipping one spin, it's very funnel-like, right? Because if you start with this, you cannot flip anyone else.
Yeah, so that there's a lot of funnels, and
Yes.
the actual minima is something you might miss out.
Yeah, absolutely. That's possible.
Yeah.
That's possible.
So, I don't see like the intuition of using this sort of approach for this problem.
No. I think he's asking, does the energy landscape need to be like very smooth for this to work?
No, it's more like the true minima has to be like much lower than the other local minima.
But that's by definition, right?
So actually,
Much
the minima is not very low, right? Compared to actual
In
minima.
this sort of energy thing, any allowed configuration also has a very low energy, and the
Right.
true one that optimizes distance
Yeah.
has a slightly lower energy than those,
Right.
which is why it's.
See, you cannot find the global optimum. Like this is an NP hard
So
problem.
there's a theorem which says that
Yeah.
if you do this cooling infinitesimally slowly,
Huh.
you're guaranteed to get the global minimum. But of course, in practice, you can never go infinitesimally slowly.
I
You
see.
have to always keep a finite cooling scale.
I see.
There's a theorem which says that in principle, if you do it like very slowly, so basically the time goes to infinity, you are
Simulated
guaranteed
anyway.
to reach global.
I see. No, actually, while simulating, I did observe this. When I did this one, it's still bad. Okay, I mean, this could have been better. But if I cooled it a little faster, it was worse. If I cooled it a little slower, it was giving better. Yeah.
Wouldn't changing the parameters of the energy function change how the true minima is, how much stable it is than the other minima?
See, the terms in the TSP, the first couple of terms are guaranteeing that it's a valid tool, right? So there you cannot tinker much because it has to be a valid tool. The second one is essentially saying how to minimize the distance, and that's also objective, right? That minimum distance, even if you take different parameters, the minimum distance will be minimum distance, right? So the energy landscape structure might scale, but the relative sizes, like the true minima, will be true minima whatever constants you take.
Yeah, but I'm saying if you take some constant, the true minima would have a lot lower energy than for other constant.
For other
For other constant, it might be like this minima, but for some
definitely,
constant, it will be
definitely.
different.
So you can, if you think about this energy term, if this D is very high, it is.
So if you take enough ID, you should get the true.
No, but you get stuck. All these valid tools are actually guarded or like covered by the extremely high,
Other minima.
right? So it becomes a very like. So you can imagine a tool like this. Let's say a tool like this, right? This is also a valid tool, and it's sort of small, right? This change is the true will give you the true minima. But this particular configuration is not that far away, the energy, because this distance improvement is extremely infinitesimal, right? So it's actually
that's what you will get.
yes. So that's why it's actually very hard to actually understand which one the true minima is, because you can just change a little bit and voila, another true minima.
So you just have to make your cooling schedules.
Yes. Yes.
At that point, you're enumerating through all the
So
states.
actually, many of
No,
the
not anybody to all the things. You are near
no,
one of the
many
bases.
times actually you are okay with a satisficing rather than optimizing.
Right.
So this gives you a near optimal solution. Actually, the hardest ones to solve are the so-called golf ball landscape, where everything is flat except that somewhere you got this very deep. Because their traversing gives you no clue as to how close you are to the minimum. So those are the really tough.
Oh, okay, yeah. That is sure. This right? Oh no, I'm so sorry. I think I didn't. Oh yeah, I did. This was in 1984. So instead of the normal state update rule, where you're taking in. So one is like you look at the probability distribution of two states and then decide based on that, right? The other way of thinking of it is in terms of input. What Sitabra was mentioning in his talks, you can go from a energy difference picture to a input picture that we just saw, right? You can 1 plus PA by PB and then you reciprocal it. You get a sigmoid, right? So that is sort of like the input being received. So this is loosely based in terms of that. This is the input being received. This is a leak term which will determine, which will essentially say that the unit can either be, it has to be very close to 0, right? If it's positive, if ui is positive, this will be negative. If ui is negative, this will be positive. So it has to be close to 0. And then the dou e dou vi term, that's what it does is it gives you a certain input, and that determines if you're at 0 or are you at 1. And then after doing this, so dou e dou vi, essentially this is input, right? If you think of it in neural network terms, vj, j not equal to I, activity of all the other neurons, and that's giving you weighted sum, and then you have a threshold, and so this is actually the input. You can work it out if you just do a little bit of calculation. You can work it out, and then you're passing the vi through you're passing the ui input through a sigmoidal, so it becomes 0 or 1. Yeah. Any other question?
So you said there are better optimization algorithms. Can you mention?
There is Lynn Cunningham, which is like most celebrated, but that has nothing to do with neural networks. It's not a model. It's
Optimization algorithm.
yes.
It is just for discrete dynamics, or you can use this for continuous dynamics.
Okay, very good. It's generally for discrete dynamics. Continuous dynamics, you don't really need anything like that because it's already deterministic.
Oh, like you can do simply gradient descent.
Yes. No, it's not gradient descent, it's steepest descent. In case of deterministic, it's always steepest descent because you don't have any fluctuation in that. See, if, right? Because in case of deterministic systems, your neuronal output is taking the real value and then being fed upon, right? You pass it through the sigma and you're actually putting the real value from 0 to 1.
But there also there are optimization algorithms that reduce noise, so that if you get stuck to some local minima, you can
For continuous dynamics? Continuous dynamics?
yeah, like continuous optimization.
Okay, I'm not aware. Could be.
That is what I was thinking. Can you use
Simulated annealing in continuous dynamics. Okay, could be. I'm not sure. It will be nice if you can show me something. I mean, I'm not really sure. All right, yeah.
So thanks once again, everyone.